Our project focuses on designing a portal frame. The main parameters include a span of 30 meters, a length of 36 meters, and an eave height of 8 meters with a rafter load 40 kN per meter. Portal frames are commonly used because they provide a large clear span, cost efficiency, and flexibility, making them ideal for warehouse and industrial building. These parameters were applied consistently across both Revit and Space Gas to ensure accurate modeling and structural analysis.
The Revit portal frame structure aligns with the client's needs with 7 girts, 6 bays spread at 6 meters apart to distribute the load across the larger columns and rafters selected at 533 x 92 UB and 610 x 113 UB across the 30-meter span. The 6-degree roof for wind and rain complications is essential for where the girt's purlin sizes still offer sufficient stiffness for spans above 5.7 meters while not compromising on material wastage, also effective for the length of 36 meters. In addition to the span deck 24, the mezzanine size of 90 meters squared ensured it was in line with the structural columns and the floating platform for additional usable floor area. Secondary joints were also supported in the deck system, shown by the abundant essential floor area for the industrial setting. Structural framing connections involve the C-girt, rafter, and columns. 15 total windows of fixed and double hung ensures sustainable natural lighting and continuous fresh air flow throughout, while the large overhead door is suitable for deliveries and large loads in and out of the portal frame structure. Ultimately, the windows through to the back side decrease energy lighting costs while ensuring visibility in contrast with the 4-meter high mezzanine. The Clip Lock 700 roof sheeting is weather durable as the 50mm overhangs lessen deformation on the roof of the structure.
So today I'll be talking about the main types of load that act on the structure. First up is the dead load. This is the permanent weight of the structure itself, includes stuff like concrete, steel walls, floors, and anything that doesn't move within the structure. Second up is the live load. This is extra weight that can change, such as people, furniture, vehicles, and or equipment. We also have a combination load between dead load and live load. This is just to show engineers how the structure handles both loads at the same time. Here we have the internal crosswind. This happens when wind gets inside a structure, such as through openings or gaps. Here we have the external crosswind, also known as WCE. This happens when wind is pushed outside the structure, creating side pressure or sway. Finally, we have the internal longitudinal wind load, otherwise known as WLI. This acts along the length of the structure, for example, through a tunnel or a long covered corridor. It's important for engineers to understand these loads and how they work together to help design buildings and structures that are safe, reliable, and sturdy.
This is the review of the force combinations on the 2D model. This slide is the combination of the dead load and the live load. In the top left, it has the bending moments diagram, and in the top right, it shows the shear force diagram. This slide has 1.2 times the standard dead load and 1.5 times the standard live load with the same diagrams. This slide has 0.9 times the standard dead load plus the external crosswind plus the internal crosswind. This slide has 1.9 times the dead load plus 0.7 times the internal crosswind. This slide has 0.9 times the standard dead load minus 0.65 the longitudinal internal wind.